So, good morning, everybody, and thank you for coming here after a long night for some of you. Okay, so it's my great pleasure and an honor to introduce Zdenko Takács, a colleague and a friend. Okay, who is going to give us an interesting plenary talk about fuzzy integrals in the intervaluate setting. There are many things we can say about Zdenko, for instance, that he received a graduate degree in teaching mathematics and physics from the Comenius University of Bratislava in 1998, that he is nowadays in the Trnava University, okay, and that he's the author of more than 40 works, okay, on many different topics, many of them collaborating with us, with people from Brazil, okay. We know very well the quality of his work, the interesting ideas that he always presents, okay. He's interested in particular in topics like type 2 fuzzy logic, the handling of uncertainty, okay, and he has usually very interesting ideas and he's able to develop them in a very interesting way. So I am sure we are going to hear today a really nice talk. So Zdenko, whenever you want.
Okay, so good morning to everyone. Thank you, Javi, for introducing me and especially for very kind words. Firstly, I would like to say thank you to organizer for inviting me on this, for me, always very lovely and pleasant conference. So it is a great pleasure to be here and to have opportunity to speak. As was already told, the title of my presentation is fuzzy integrals in the interval valued setting. And here is the outline of my talk. The first part is only a short general introduction to fuzzy integrals. In the second part, I will focus on some specific features of intervals, which will be important for my further developments. These two parts can be regarded as some kind of preparation for the main part of my talk, which is interval valued Schocker integrals. In this part, the main objection, and I think it is the main objection of my presentation, is to give a review of methods or approaches, how to extend fuzzy integrals or now Schocker integral from numbers to intervals. My original intention was then proceed with the parts, with the similar parts regarding Sugeno integral and other kinds of fuzzy integrals like Schilkret or Weber or so on. But since I don't want only to give some review, but I also want to explain why and how authors treated the problem of extension. I realized that it is too comprehensive topic. So, in fact, I skip these two parts, and it means, of course, except that I'm almost in the middle of my presentation. It means that my title does not correspond with the contents of the presentation, so I changed it. I made it only here with the small letters. So now I hope that I achieved that the organizers are happy that I deliver the presentation that I promised, and I am even more happy because I can talk whatever I want from now. So let's start with some general remarks about integrals. The basic idea behind integration is a summation of a finite number of infinite quantities, infinitely small quantities. However, in my presentation, I will focus on discrete case. So it means that the situation is much completely different, and we are speaking about the summation of finite number of quantities which are not infinite. So it means that in fact I'm talking about some kind of or some type of aggregation function. So this is the point of view on my presentation, that all the presentation is settled in the framework of aggregation functions. The development with respect to fuzzy integrals are quite limited when considering only Riemann integral. However, taking into account Lebesgue integral opens much wider possibilities of developments. As you all know, the difference between the two types of integrals is that in a Riemann integral we use partitioning of the domain, while in Lebesgue integral we use partitioning of the range, and it also means that in Lebesgue integral we apply some measures of some subsets of domain. So I can say that Lebesgue integral strongly depend on measure, and it is the wide range of possibilities how to choose particular measure with particular properties that makes Lebesgue integral so flexible and strong or powerful framework for integration. Probably the most important or interesting property of measure with this respect is additivity, or maybe better say non-additivity. Because taking additive measure, the Lebesgue integral leads to calculation of weighted mean or weighted sum. However, taking non-additive measure, we obtain a nonlinear and continuous aggregation function. So this is what we call Schocker integral. It can be regarded as some kind of generalization of weighted sum. In a similar way, Sugeno integral can be considered as generalization of weighted maximum, but I'm not going to talk about Sugeno, so can skip this. Some notation, we will work in a measurable space where X is a non-empty universe. A is a sigma algebra of the power set of X, and we will integrate some measurable functions. So the function f is function from X to unit interval. It can be regarded as fuzzy events. And finally, a fuzzy measure, it was, I think, presented on this conference too many times, is a non-decreasing set function from A to the unit interval, which is grounded and normalized. So from one point of view, the fuzzy integral can be characterized as a monotone extension of fuzzy measure. From other point of view, it is often defined as a monotone functional from F to unit interval, which satisfies this property. Here in this definition, we don't see any mention of fuzzy measure. However, it is implicitly there, and we can construct it in this way. So this is some general point of view, and in discrete case, which is in my case more important, I can significantly simplify the notation. So what we will really use is that instead of finite universe, I will work only with the set of indices. Then, of course, the sigma algebra is the power set of n. In this case, the function from n to unit interval can be represented by a vector. So instead of talking that I'm going to integrate some function f, I will in some sense calculate an aggregation function of a vector x. And of course, fuzzy measure is from power set of n to unit interval. So this will be notation during my presentation. I think I need not to comment this definition. It is the basic definition of Schocker integral. I only want to stress this thing that we need to reorder inputs, and the ordering of inputs is doing throughout this permutation sigma. So this will be crucial for my next steps. some relations between Schocket and Schocket integrals and some classes of aggregation functions. If we have the set of all fuzzy measures and subset of additive measures and subset of symmetric measures, the only measure which is additive and symmetric is this measure, which is cardinality divided by n. And from the point of view of functions, it means that we have the set of all Schocket integrals, we have the subsets of all weighted arithmetic means, or additive Schocket integrals, or linear. We have the subsets of all operator or symmetric Schocket integrals. And again, in the intersection, there is the only aggregation function, which is weighted arithmetic mean or which is additive and symmetric, and it is arithmetic mean. Okay, now another very short part about the specific features of intervals. So with respect to notation, I will denote by L01 the set of all closed subintervals of unit intervals, where the intervals will be denoted by capitals with this lower and this upper bound. I will focus, or when we work in interval settings, we always should focus on some specificity of intervals. First of them, of course, is a order, because the natural order of intervals is partial. I think I will talk about this a lot in a few minutes, so now I need not to add any more. The second thing with respect to intervals, it's width, because the width of intervals is always somehow connected with uncertainty, whether it is uncertainty of our knowledge or of the object itself. It is not so important for us now, but always this width of intervals give us some additional information comparing to working only with numbers. And finally, what will be important for me, that when I want to extend some function from numbers to interval, it is some kind of proper extension if it satisfies the property that when the inputs are degenerate intervals, so the results of interval valued functions should be the same as the results of original function. So these three things will be for me important in the next part. Okay, now I focus only on order from these three things. I think you all know this order of intervals. It is based on the comparison of lower bounds and upper bounds separately. Clearly, it is only partial order. What it means that if I represent intervals as points of this triangle, the green triangle. So it means that here are intervals which are greater than x, here are intervals which are smaller than x, and here are intervals in the brown parts which are incomparable with this x. So of course, the need of total order motivated authors to many approaches, and I think that in this paper in 2013 was given some generally accepted framework for total orders called admissible orders, which simply is defined as a total order of intervals which refines the partial order. Graphically, it means that you should keep this green part so that it would be in line with the partial order, and you can define in this brown part whatever you want, but you have to achieve that at all it is total order. The important property of these admissible orders is that since these red points, so interval 0, 0, and 1, 1 are in the green part, it means that each admissible order will have as minimal element interval 0, 0 and as maximal element interval 1, 1. Probably the most often used class of admissible orders now are the orders based on this K-alpha operator. The K-alpha operator is defined as it takes as argument interval, and the result is some weighted mean of its bounds. And based on this, the K-alpha beta order is defined as in this way, that x is less or equal to y if and only if k alpha x is less than k alpha y, and if these k alphas are the same, then we compare the k betas of this interval. So in this way, we obtain some total order, and maybe I can skip this, I think. Okay, so now I begin to focus on my goal, and I'm going to speak about interval value shocked integrals. Again, very short introduction. These are four things that I'm going to focus on in each method. The domain and range, of course, this is clear. It only means that I'm going to change the unit interval by L01. Here only notation. From now on, always the standard C will mean the standard shocked integral. By standard, I mean shocked integral for numbers. And this double C means the interval value shocked integral, so for integrals. When I extend shocked integral, firstly, I have to decide if I am going to use standard fuzzy measure, and again, by standard, I mean that the results of the measure are numbers, or if I'm going to use interval valued fuzzy measure where the results are intervals. As we will see, mostly authors still use this approach. Only in one case there will be used the interval valued version, but this is discussion what is needed from the point of view of application, and I think this is more natural, at least now. The most important thing to decide is if I'm going to work with partial order or with total orders, and as we will see, when I decide for total order, then there is a question which of them, because there are infinitely many of them. And finally, what will be important for my developments is to decide which expression of shocked integral I'm going to use, because here we can see three different expressions of shocked integrals. The first one is the definition that I gave a minute ago. This is some different expression of the same, and this is expression based on Mobius transform. You know probably that all the three expressions are equivalent in numbers, but this is not true for intervals. So when I'm going to extend to intervals, I have to think which expression I will consider. I will refer to these expressions as x minus x, because here is the difference of inputs, m minus m, or map. This will be my abbreviation of these three expressions. Okay, this is my favorite slide. This is the review of approaches of various authors from various papers, where they focus on extension shocked integral from numbers to intervals, or on definition of some kind of interval valued shocked integral. I try to make some order in this. First, I divided them to two parts. Brown are with respect to partial order, the green are with respect to total order. And now my goal of this presentation is to go step by step each of these approach and to say a few words about it. to show definition and maybe some comments about its advantages, disadvantages, or something like that. So I will start with the first approach, which is based on the notion of Allman's integral for set value functions, and it was in 1965, and it was then adapted in 2004 for Schocker integral. It is the very simple definition. I will always denote the interval fuzzy integral with this number, so it is the first approach and so on. So it is defined as a set of standard Schocker integrals where the inputs of the standard Schocker integral are the numbers from the interval. So this is very direct definition. In this case, there is no. It is not important which expression we use because we only calculate standard Schocker integrals, so they are equivalent. So this is not important, and we implicitly use here partial order. Of course, this can be simplified because the Schocker integral is continuous and monotone, so I don't need to calculate all the functions, all the values. I only need the Schocker integral of lower bounds and Schocker integral of upper bounds separately. So this means that this is called representable interval valued function because it can be calculated by two functions separately for lower and upper bounds. This is the generalization that I told about. If we have inputs degenerate intervals, then the result is, in fact, a standard Schocker integral. I will repeat again and again this property, so all the approaches that you saw in the list satisfy this property. Okay, what is advantage of this approach? The maybe main advantage is that it is very simple and even we don't need to consider any order of intervals. Of course, if this is advantage, very same is also disadvantage because if we don't consider any order of intervals, it means that in fact we do not consider ordinal structure of the data. So something is missing in or we are missing some information which is important in interval valued setting. So this is the reason why so many authors are trying to define Schocker integral with respect to total order, as we will see later. So the second approach is based on Möbius transform. I think again I can very quickly skip this. If we have some fuzzy measure, then this is called Möbius transform of this fuzzy measure, and based on this transform, we can define interval value Schocker integral, or in this paper it was made as a direct translation of expression based on Möbius transform. The only distinction is that here are intervals now. Since if you look at the definition, we don't need reorder the inputs. So in fact, we don't have problem that we have only partial order. In fact, the order is hidden in this minimum, but it is used or it is applied like mid operation of lattice structure. So in this way, we can obey the problem of incomparable intervals, and we have the definition of interval valued Schocker integrals. Again, the generalization, I will only say again, it means that is all. The third approach with respect to partial order is based on this paper. In fact, the authors in this paper deal with OVA operator for fuzzy sets. I only adapted the procedure to intervals and to Schocker integral. It is, I think, very simple idea. They took some, it is based on this lemma where we have a vector of some elements of complete lattice, and by these simple equations, we obtain a corresponding chain of elements from the lattice. And the idea of the authors was that they defined an interval valued function in such a way that they replace the real inputs x1, xn by the new inputs z1, zn, which are obtained by the lemma and which form the chain. So in this way, we don't need to reorder z because they already form the chain. So we can skip sigma here, otherwise the expression is the same as the original one. So in this way, we obey the problem of non-comparable intervals because we have chain. Of course, with this approach, we should be careful because in fact we are using some different inputs that were originally made. So we should somehow know that we can do this, or we are not losing too much information if we are replacing the inputs. Again, okay, these were the three approaches that I found in literature with respect to partial order. But for me, the more important are approaches with respect to total order. So let's start with them. The first one, which is called 4a. This is only direct translation of the expression m minus m for the intervals, because now if we have some admissible orders, so we have total orders, so we are able to reorder the inputs always. And we can use this expression. Why this expression? Because here we have difference of numbers. The measures are numbers, which is not problem. The expression x minus x makes problems because the difference of intervals is not closed in L01. So this is the maybe most problematic operation from the operations that are used for Schottky integral that we are not able to directly translate the difference of the numbers to intervals. So this is very direct approach. What is again, it is generalization, and it gives the same results where the inputs form the chain. But what is important, that advantage of this approach is that since we consider the total order, we somehow consider also ordinal structure of the data. What is, I gave it like advantage, but I'm not sure if it is such good advantage. Each admissible order generates specific interval value Schottky integral. So it means that we have infinitely many possible admissible orders. So we can define infinitely many interval value Schottky integral. Of course, this give us the wide possibility of choosing, but on the other hand, the question arises how to choose admissible order, which I want to consider. So this is the crucial task to solve if I want to use this approach. And for this reason, another two approaches were proposed, which solves somehow this question. So now I will somehow continue in this direction, and I will show how in this approach 4b is solve the question how to choose admissible order. This approach is based on the notion of admissible permutation, which was defined in this paper in 2019. And simply idea behind this, if you have fixed some vector input vector, so you have intervals x1, xn, you don't need to consider all the possible permutations, but you only need to consider permutations which are in line with the partial order. And in fact, this is what is called admissible permutation. I will explain on very simple example. We have 5 intervals with this Hasse diagram. In fact, there are 5 factorial possible permutations, but from the diagram, we can see that only 2 of them are admissible because only 2 of them are in line with partial order. and it means that we should only consider two different orderings of these intervals. And this looks like the notions of admissible permutations and admissible orders are the same, but this is not true. There is very important difference because admissible permutation is defined for some fixed vector of intervals. So it means that from one point of view, if you have fixed vector of intervals, then each admissible order induces admissible permutation. But in the opposite way, for each admissible permutation, there are in fact infinitely many of different admissible orders. So by this way, authors try to somehow reduce complexity of the problem of ordering. And so in this paper, was defined this interval valued Shocked integral in this way that we calculate the Shocked integral from the approach for A with respect to order which is induced by permutation sigma, and we take all the permutations from this is the set of all admissible permutations. So in the previous case, we would have two results because we would have two admissible permutations. What is advantage of this approach? Yes, we have. Okay, just generalization again holds. This is again the same results if the inputs form the chain. But what is the advantage of this approach? That it keeps all the advantages of the approach for A. And moreover, it solves the problem how to choose admissible order. On the other hand, what is maybe not so good is that the number of admissible permutations still can be very large. So it is the reason why we propose another approach, which again continue in this line, and in this approach, we try to find something like base admissible permutations. So we have some set of admissible permutations, and we are going to choose one or more, which we will call the best. There are more technical details in this paper from last year, so I only very softly say about them. The comparison degree. Firstly, we define the comparison degree, which means that we take two intervals and assign them some degree of comparison, which says how good the intervals are ordered with respect to partial order. I will explain it an example later. Then, according to this comparison degree, we defined so-called degree of totalness of admissible permutation of sigma, which is a degree which takes some admissible permutation and assign to this permutation some vector. Again, I will show it on example, but we use this degree of totalness for definition of partial order, because if we have assigned to each admissible permutation some vector, then according to these vectors, we can somehow compare the permutations R, and if we have, it will be the partial order, and if we have the partial order of the permutations, we can choose the set of best of them with respect to the partial order. So again, some simple example. We have for intervals which are ordered in this sense by the permutation sigma. This means that the sigma is admissible permutation because it does not alter the partial order. What it means that the first two intervals are comparable with respect to partial order in a good way, and these three are incomparable, so they do not make problems with respect to partial order. Now, we take the first two interval and assign them the comparison degree. In this way, or in this case, if the intervals are comparable in the correct way, it means that comparison degree is 1. And this comparison degree decreases, very freely said, if the intervals are not comparable, and it decreases more and more when the intervals are far from being comparable in a good way. It means that if you look on these intervals, it is really very intuitively only. If here is 0.6 and we should increase it to 0.7, then the intervals would be comparable. In this case, the intervals would be comparable only if we increase this 0.1 to 0.6. So there are more far from being comparable, so comparison degree is less. Okay, and then we have comparison degree of all the neighbors of pairs of intervals, and then we define the degree of totalness as a vector which takes values of these comparison degrees. And according to this, we define the partial order and we choose the best of them. And then we defined the interval value choquette integral called for C in the same way as for B, but here is the only change is that here is not the set of all admissible permutation, but the set of best admissible permutation. This means that again, we keep all the good properties of approaches for A and for B, but we significantly reduce the complexity of computation because we only need the best permutation, not all of them. Again, generalization, again, inputs. This is the reason why I gave these three approaches together, because they are somehow connected. So next approach is based on the notion of dissimilarity, and it takes expression x minus x, was defined in this paper from 2022, and replace the difference of intervals by dissimilarity. The motivation was that the difference of intervals was problem because it is not closed in L01. So it was somehow generalized because dissimilarity is some kind of generalization of difference. Again, very intuitively said. Maybe some kind of generalization of symmetric difference, but since we have chain, it is not problem for us. So in this way, the interval choquette integral was defined, and here, okay, what I can say is that again we can use the very same procedure. This was not done in the literature yet, but we can use very same procedure as we used here. So anyway, what I want to say that this approach for B and for C is a general approach to choosing of admissible order. So in any situation when we are working with admissible order, these two steps can help us to choose admissible order. So as I used it here, it can be used also here. Okay, and final approach. In fact, this was not made in literature. This was only inspired in this paper of 2018, where we studied the interval value negations, and there we proposed construction method based on these notions that are defined here. Again, some simple explanation. If we have some fixed value C, then all the intervals whose k alpha is equal to C lays on this line segment, and the slope of the line depends, of course, on alpha. Now, if you look on this line, then this interval, what is the color? Blue, is degenerate interval. It is CC, so its width is 0. And when we are moving along the line, the lower bound decreases and upper bound increases. So it means that the width of intervals increases along this line linearly. And so we defined first the notion of maximal possible width, which means that it is the width of this red interval on the line. And then we defined lambda alpha x, which is the ratio between the actual width of the interval and the maximal possible width. This means that for this blue interval, the ratio is 0 because the width is 0. And for this red interval, it means that lambda is equal to 1 because this is the same. So using these ideas, the interval Choquet integral can be defined in this way, that the result is interval z, about which we have two informations. The first one is that k alpha of z is equal to standard Choquet integral of k alphas. And the second one is that the lambda alpha is equal to some aggregation of lambdas of inputs. This means that this approach is somehow different from the others, because in this way we treat separately some important point of the intervals. This important point is based on the notion of the choice of alpha. If alpha is 0.5, we choose the middle of the interval. If alpha is something else, we are talking about some different point. So we separately treat this important point of interval, and we separately treat the width of intervals, because the lambda is connected with the width of intervals. So in this way, we are able to control the width of result according to the width of inputs, which is in some situation is important. So this is the last approach that I wanted to present. Again, the generalization hold, and as conclusion, I only want to somehow summarize the results. So we have many approaches to this problem of extension of Choquet integral to intervals. Of course, these approaches can be applied with more or less adjustment to other intervals or to other interval valued functions. So these methods are mostly general with some adjustments. What are, from my point of view, the two most important things are, of course, reordering of the inputs, and the second is difference x minus x, which is in fact the only problematic operation in the definition of Choquet integral. So I showed how these approaches treat with this problem with respect to reordering. The approaches with respect to partial order treats it in the way that the first approach, the Amman's approach, only calculates the Choquet integral for numbers, so we don't need to reorder intervals. The second approach uses expression by Möbius transform, where again we don't need to use ordering of the intervals, and the third approach replaces the inputs by the change. So again, we can order the inputs, and the rest, the green ones, which are with respect to total order, there is no problem with reordering. There is just problem how to choose which order we can use. But I thought about this a lot. And with respect to difference, again, there are each approach treat this problem in a different way. The first and the last approach calculate only Choquet integral for numbers, so we there don't have difference of intervals, so it is not problem. Expression with respect to Möbius, also there is no difference, so we don't have problem. And these are three. Number 4 uses expression m minus m, where m's are numbers, so again we don't have difference. This approach uses that it replaces the difference by dissimilarity. So this was the solution of the problem. And finally, in the third approach, we have difference of intervals, but we replace the inputs by chain and difference of by chain with respect to partial order. So the difference of intervals which form the chains is not problem in L01. Okay, so this is all from the point of view of Schocker integral. And finally, only very short information about Sugeno integral. This is really very free formulation of some fact, which I think all of you know very well, that you all know what is Hirsch index, and you also know that this index is in fact Sugeno integral with respect to some special fuzzy measure. So having in mind this, that here index is equal to Sugeno integral, I want to only formulate one hypothesis, which can be regarded as open problem, but I'm not going to comment this in any way. So please just read carefully by yourself. You will have only a few seconds.
Thank you very much, Denko. We have time for some questions and comments. So somebody has some comment, some question, please.
Thank you very much for interesting talk. My question is, for example, if I have some extension of integration of stochastic processes, there is like a reference point expected value. So it means that if I have expected value for each, say, for each random variable at each, for example, time, so there is like link between the integration of stochastic process and the expected value of the result and the standard Lebesgue integral of this function, which is like expected value at each time. There is something similar for this approach. So it means that there are some reference points in each, say, interval, so that it means that I am able to compute the Schocker integral for intervals, and then I will find this reference point, and it is the same like the Schocker integral for such reference points. For example, admissible ordering has some points.
So I think maybe you are referring to this last approach. I'm not sure because I didn't think about it in this direction. I don't know in which stage you want to use the Schocker integral.
For example, I take the middle point. Okay, so I will order according this middle point using probably another one. So then I compute the Schocker integral. So my question is, for example, if the middle point of the result will be Schocker integral of this middle point, so something like this. There is something. Bizarre.
Yeah, I think this last I think this could be used because in this point you calculate exactly what you are saying, and the question is how will behave this width of the intervals, because by choosing this aggregation function you can choose how how you will, or you can control the width of the inputs interval. So if you have some middle point of the expected value, you have to think what is your input interval. I don't know what you mean. And there, how you want to treat with their standard error or width intervals.
Thank you very much. Some more questions, please, Ratko.
We have several properties of Choquet integral or standard Choquet integral, which could be discussed for which extension to intervals it works or not. For example, if we take dual Choquet integral, we know that it's Choquet integral with respect to dual measure. Or if we take belief function, we know that it's infimum of standard Lebesgue integrals with respect to probabilities corresponding to the core. Do we have something similar? Maybe not in all of your approaches you have presented, but in some, yes, in some, not. So some comments to this.
Oh, to be honest, I don't remember something else. I would say no, but only fuzzy no. I'm not absolutely sure, but I don't remember that I saw something like this. What was done? Yes, but yeah, there is also a question of the measure. I forgot to say it in this approach. In this one approach, we can use also the interval measure. So if we want to use some dual measure, then I think with intervals it will be maybe more problematic than with numbers, because what I didn't commented the properties in these approaches. Of course, the monotonicity is not generally satisfied. So in some approaches we have some strong conditions under which the monotonicity holds, or we only have some pre-aggregation function with some directional monotonicity holds. So with respect with duality, I think it will be quite complicated.
Okay, thank you very much. Some more questions, more comments. Somebody? If not, I have one question. Okay, in the last approach you have presented, you discussed the possibility of controlling the width of the intervals, because that's important from the point of view of the applications. Have you made some study in the previous cases if this width is preserved somehow? You know, if, for instance, the width of the output is smaller than the width of the inputs or bigger or somehow like that?
Yes, but don't know in which. I don't remember for which approach. Yes, we made some conditions that we wanted to keep the width of the result. I think the less or equal to maximum of the width of inputs, or as maybe not it should not be less or equal to maximum, but it can be also some product with maximum.
Yeah. If not, in some sense, maybe it would be interesting to use some work by Tiago and Grasalis, okay, when we saw how you can try to build some aggregations, maybe some of these Choquet integrals, I'm not sure if they're all controlling the way in which the width of the intervals is changing. And that can be interesting from the point of view of applications.
Yeah, I know the work, yes.
Okay, some more questions, remarks? Nobody? Then, if so, we thank again the speaker for a fantastic plenary talk. Thank you very much.